Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 10. Students, in this lecture, inshallah, we will discuss the last session of our flat slab design, and this is just an introduction and control techniques, different techniques are controlling methods of punching shear in flat slabs. Okay, so this important is very important because in lecture number 11, inshallah, in coming lecture, I will do an example on it. Okay, so that's why I'm just trying to explain a little bit theoretical portion of the punching shear and its various techniques. Okay, so let me show you something. Okay, what is basically a punching shear? Okay, you see in this picture, basically due to the self-weight superimposed load, live load basically, and due to gravity, the slab basically you see it tending to move in downward direction, or you can say it moves in downward direction due to gravity. So due to gravity basically, and the column you see that is standing at own place, so the slab basically trying to move down in the downward direction, and you see that the column basically it penetrates into the slab, and it's you see the head, this head is just like a pyramid. Okay, and basically here the column do not move, it should be remembered, only the slab moving in downward direction. Okay, and this is all due to punching shear. Okay, the reason behind this kind of failure is punching shear. Due to punching shear, basically this kind of failure is occurred. Okay, so this punching shear is very important to understand and how to control it. Different techniques we have, and remember, this kind of failure is basically dominant where in the lower story of your building, basically where car parking is allowed. When there is 2 to 3 car parking in your basement of your structure basically, so due to that heavy concentrated and heavy live load, this kind of failure is very dominant, and you have to provide such kind of arrangement to control this kind of failure. Okay, so you see column drop panels are provided, column capitals are provided. This is basically needed. There is no column capital because they are upper stories. In upper stories they are not such a greater amount of shear punch. Okay, punching shear. Similarly, you see this is a car parking, and heavier drop panels are provided. Why? Because there is a huge amount of punching shear. Similarly, the failure you see that the slab is moved down. Okay, due to punching shear, the column have a pyramid shape you see, and the column are at own place, they do not move while the slab moves in downward direction. These are different techniques. Inshallah, we will discuss it. And let me start the lecture. So remember, we have basically session 2, and in session 2 we have to cover these topics. We have flat slab system, and we have flat slab system. This is very important to understand. In flat system we provide column capital, we provide drop panels, while in flat system we do not provide such kind of capitals and such kind of drop panels. So in this kind of slab, basically shear punch we control by using internal techniques. Here this is a kind of we can say external technique, that we are externally, when we are not able to control the punching shear that is very huge, very large, and it cannot be controlled by the by column capital and drop panels, not be controlled by by integral beams and shear studs and shear heads. What they are, inshallah, I will explain those techniques. So then we provide this kind of external techniques. Okay, and here you see basically we have to control the punching shear by internal techniques. Okay, this is the shear punching shear crack which is developed from the face of the column. Okay, and we basically consider a section, a critical section at a distance of d/2 from this face as well as from this face. So d/2 and d/2, what it makes, for example, let me show you this. This is my column, and this is the column panel which it supported. Okay, this is the tributary area, you can say, of the column. So this crack is d by 2 to this side, d by 2 to this side, d by 2 to this side, d by 2 to this side. So basically it forms a critical parameter, and you all know about critical parameter or critical area, critical punching shear area. In footing design you will understand it. Okay, so this area is basically very important. This area is very important. Here the shear punch is it is at its worst stage. Okay, so you see this diagram, shear crack is developed, and this is pyramid shape. Basically it go in upward direction while the slab moving in downward direction. Here you see clear. And this is a common beam example. Okay, the shear crack is basically developed at a 45-degree roundabout approximately, and critical section for which we basically design our stirrups VCR, it should be considered at a distance of D. Okay, and remember this is the tributary area for the column which basically exerts shear. Okay, VU. So we will discuss it in later, but remember this area is basically important. This is the area, this is the critical area. Okay, and we have to determine it. This area is very important. Okay, this is known as an art. Okay, and we must determine it. Okay, this is very important to understand that for various columns, like this is the interior column, this is the edge column, this is the corner column, how we determine what will be the side of our critical parameter and what will be the critical area. This is very important. So you see here, this side of the critical parameter will be this side size. Let's say this is C1. So C1S means shorter side of this column, C1L means longer side of this column. So this side will be C1S plus this half D by 2 and this half D by 2. So you gain C1S plus D, because D by 2 plus D by 2, if you take LCM it give you D. So that's why he write down C1S plus D. And as it is, we have two sides, so therefore they multiply by 2. Now we have to find out parameters, so we need this side as well. And this side is also equals to C1L plus D. If it is a square column, then it will be equals to C plus D. Okay, the critical parameter will be look like it 4 into C plus D, and its critical area and art will be, if it is a square column, then it is sample C plus D whole square. Okay, if it is a square column, and if it is a rectangle column, then you have to multiply these terms C1S plus D into C1L plus D. Okay, then you have to multiply these two dimensions. It will give you critical area NR. Remember, I will use this formula in my example. Similarly, for H column, you can determine it. Okay, in H column, you have 1, 2, 3 sides. Now, 2 equal sides, 1 different side. So that's why they are using this one. And if you are interested to find out the area of this critical area, so this side times this side, this will give you the NR. Okay. So this is not complicated. This is for corner column. You have just only 2 sides, and you just multiply these 2 sides with each other. You got the critical area, and the critical parameter will be this length, and this length will be equal to this formula. Okay, and this is the tributary area. The shaded area is the tributary area. How we can determine it? Okay, remember, from the face of the column, we will determine from center to center distance in between these adjacent columns. Okay, then we divide that adjacent columns for this side, we divide it by 2. Okay, this is L2 by 2, and this length is L2 by 2, L1 by 2, sorry. This length is L1 by 2 up to this point, and up to this point, this length, you see, this is L1 from this center column to this center of the column. This is also L1 by 2. Similarly, this will be the whole length, which is denoted by L, and similarly in this direction, this length should be this length from the center of the column to this one, L2 by 2, and similarly this length to the center of this column is equals to this length. This length will be L2 by 2. So you add L2 by 2 plus L2 by 2, you got L2. So your whole tributary area will be, now remember, once you multiply your L1 with L2, you got total area. If you are interested to find your tributary area, then you need to subtract your NR, that is the critical area, from your whole area. This will be now your tributary area, and if you are interested to find your VU, then you need to multiply it with your WU, that is the per square feet or meter square loading, ultimate loading with your tributary area. It will give you the shear. Okay. After that, we need what? We need to calculate the pi VC, that is the shear strength capacity of our concrete. And you all know this equation which is used in footing design. So your shear capacity of your concrete and slab will be equals to this one. This formula beta C is basically nothing. It is the column longer side to shorter side ratio. Okay, and for a square column it is equal to 1. Okay, so and alpha S is basically is also a factor, 40 for interior column, 30 for edge column, and 20 for corner column. So you have to just plug B naught is your critical parameter and is your effective depth. So you have to calculate the values of these three equations, and you have to select the minimum one. Clear? That will be your punching shear capacity of your concrete. Now what further you have to do? You have to compare your shear punching capacity or shear capacity of your concrete against your VU. If it is greater than this one, so you are okay, you don't need any kind of shear reinforcement. If this case exists, then you have to use different arrangement to control your punching shear. For that purpose, if you have a flat system, remember these three techniques are used in flat system. Increasing depth of slab, you have this one option. You can increase the depth. Okay, so depth can be increased for the whole slab as well, or either you can provide for a drop panels. Okay, and let me show you in this video. You see in this video that how they basically control the punching shear capacity. Okay, here we have, remember these are the techniques. In one picture you can understand that one time they provide basically beams. You see, either by providing beams, so as in flat slab beams are not allowed, so that we can't use beams. The other option is column capital. You can provide column capital. Okay, by column capital you can control your punching shear. Then the other option is drop panel. You can control it by drop panel. The third option, or the fourth option, I think so, the third option, this is by increasing the thickness of your slab. So you have these kind of arrangement to which you can control your remember that basically, yes, you are increasing depth, then increasing your B naught. Now if you are interested to increase your B naught to, for example, as you seen picture basically here, let me show here, here if you are interested to increase, to extend this B naught to this point, then you have to use such other interior treatments, interior arrangements, interior techniques, internal techniques. For that we are basically providing different arrangement, like the provision of integral beams. Now what is integral beams I am explaining. Okay, so the critical parameter can be increased, and the third option is that you need to increase your FC fry. So these are the techniques through which you can increase your B naught. Now you can easily provide your integral beams. What is integral beams? Let me show you. Remember, in this video you see, in this picture you see, this is integral beam. So just like a ceiling beam, as you see ceiling beam in your RCC slab, so this is the beam basically which increase your critical parameter, because you all know the shear crack develop at an inclined angle. So the vertical legs of these stirrups basically preventing that shear crack. Okay, you all know this principle in your beam design. And basically what we did, in the calculation, in lecture number 11 I will do an example on it. So we basically determine the length of the horizontal bars and the amount of the area of these vertical stirrups and the spacing of these stirrups, that how to control basically that kind of shear. And this is the way how shear, basically punching shear crack develops. You see the slab moving downward direction and column in upward. Okay, and here you see this is column capital. Column capital is this one, and drop panels I already explained, and this is also drop panel, and this is known as shear studs. Okay, this is known as shear studs. This is very important. a steel beam, I beam, W shape, S shape beams is basically provided at the column place, and this greater amount of shear capacity can be increased of the concrete. And remember, it also play its role in basically in negative bend, negative flexure as well. Okay, it also control your flexure. And the next one is, this is also an arrangement. You see the column in middle, and these I beam is basically provided, and this bent up bars basically you see it in different location. They provide bent up bar here, they provide bent up bar here, so that the purpose of this to control the crack. These I beam basically control the crack, this bent up bar control the crack, this bent up bar, and similarly further they provide beam as well. So the key function of this kind of arrangement, similarly you see as free stress bars is also provided. So this is a very high amount of, when you have high amount of punching shear, basically we do this kind of arrangement. And one thing very most important I want to share with you, these are the shear studs. These are known as shear studs, and they are, you see from the face of the column, they are radiating. Okay, so how we provide it, there are different techniques. Basically it can be provided in the, look, in a footing, you see the depth of the footing is increased, is larger. Okay, if you are entrusting to control your depth of footing, the mat footing, basically the mat thickness, it is, if it is a larger and you need to control it, okay, and you're entrusting to provide a smaller amount. So by placing those shear studs, remember your footing depth, or you can say your mat thickness will be decreased. This is the shear studs which we are using in upper stories, and they are radiating, and the vertical, these studs basically prevent the shear cracks from developing. Okay, so this is how basically that we can, and remember, look, when they place those shear studs, the load 4 ton extra loading can be applied. This means that it can increase very huge amount of shear punching shear strength, okay, of the concrete. And similarly you see the flat slabs, and okay, so this kind of arrangement is needed nowadays. Okay, people demanding for basically for flat slabs, okay, because it looks beautiful, and there is a flat smooth surface. Okay, so, and its sealing will be also easy. Let me show you another interesting video, that is a very important video for you people. This video shows the detailing of integral beam. Okay, how you have to control provide integral beam. Okay, remember this is integral beam to 4 sides of a column, and in calculation we need to determine the horizontal length as well as the stirrup area. Okay, so you see these stirrups are, so how congested they are, and how there is a huge amount of shear, you can say. So in this video basically you have to focus on this stirrups. Okay, and one thing which is most important, and this is very important. Remember here you see 1 2 3 4 5 and 6 legs of the vertical stirrups. Okay, so basically they are using 1 2 3 stirrups, 3 triple stirrups, and 6 legs. So if this is number 4 bar, so number 4 bar is 0.19. So the total shear area in this beam is 4 times 6 times 0.19. But remember these stirrups are placed along the 4 sides, because we have 4 beams, as you see here in this video, that one beam here, one beam here, one beam that one, and one beam that one. So we are placing basically these stirrups in 4 beams, so that by the total shear area will be 4 times 6 times 0.19. This is very important to understand, and I will use this in calculation. Okay, in example here you see the detailing of this beam, that at the column edges you see here, and this is the full detail of you see 1 2 3 4 beams, and the detailing you see here, that in each beam you have to provide 12 stirrups. Okay, and those stirrup spacing is 3 inch center to center, and you see here, and similarly the legs 1 2 3 4 5 6 legs, and these are the shear area, and 6, remember, if you have 6 legs, basically this means you have to provide 6 horizontal bar, and the same bar as those which you are placing for your flexure control of main bars of your flexure. So same bars you can place. Similarly, 6 bar down and 6 bar in up portion. So that's why you have to place total 12 horizontal bars. And here you see triple stirrups, means you have to provide 6 legs. Okay, triple stirrup means you have to provide 6 legs. Okay, and this ends up, let us these are the techniques and how we can design basically a drop panel. So the design is simple: the length which is to this side divided by 6, and the length which is to this side divided by 6. So it will give you the total length of your drop panel, and it will be, if it is a square, so then LA plus LB divided by 6 to this side, and similar to all other 4 sides. Okay, the thickness according to ACI limitation, this should be equals to HF divided by 4, but not should be less than 2 inches. Okay, and the drop panel design is also simple. We have to fix this. Remember, in drop panel design we need to determine this Y, this height, and its modified diameter, or you can say the side if it is a square column or rectangle. So we need this side. This is denoted by C. So how we obtain, inshallah you see an example how we determine it and how we determine this Y. But remember, the angle should be less than 45 degree. Okay, I will explain this thoroughly in example. Okay, and the next thing is the design of your integral beam. Remember, if you are interested to provide an integral beam, remember your effective depth should be at least 6 inch, but not less than 16 times the diameter of the shear reinforcement. Okay, this is very important. If you are providing, this is the minimum requirement, that your effective depth will be equals to 6 inches. When bent up bars and integral beams are used, ACI reduces pi VC. This is very important. As you see, we compare pi VC against VU. Okay, VU. But when you are providing such kind of bent up bars or integral beams, then you have to half this. Half strength of the concrete should be considered, as we did in basically in shear reinforcement design of beam. In integral beam design, this is very simple. You have to find out your vertical stirrups, dia, spacing, and in horizontal beams, okay, that for what will be the amount of steel and for how much distance. Remember, this distance is denoted from the center line. From the center line, this distance is denoted by LV, and we are interested to find out this length. Okay, how we determine this LV? It is simple to determine. You see here that the total distance is denoted by LV, and from the face of the column up to this width, this is critical parameter, sorry, this distance is denoted by X. Remember, this distance is denoted by X, and this X is equals to 3 by 4 times LV minus C by 2. C is the size of this column. Okay, if it is a square column, then all the sides C by 2 and C by 2. Okay, but if it is a rectangle column, then one C will be different. Then will be C1 divided by 2 and C2 divided by 2. Remember, and in case of circular column, then you have to consider it as a D. Okay, it should be a diameter of the column. And remember, this inclined sides, we have 4 inclined sides: this one, this one, this one, and this one. Okay, we have to extract this triangle. Okay, we need to extract this triangle and find this inclined R. Okay, this is denoted by R, and we have 4 R's. You see, 4 R's. So the total critical parameter, then beta naught, will be equals to this R, 4R. Okay, we determine 4R plus, you see, this distance you have to add up. This distance is basically nothing. It is equals to the face of the column, that is C. So we have 4C, 1, 2, 3, and 4. This one. So we have to add up this 4C. So once you got your R value, here you see, you got your R value from this triangle. Your R will be equal to x square plus x square in the root. Further simplify this, it will be equals to 2 under root into x. Okay, into x. So just plugging the R value here, you see R will be equal to this one, R will further is equal to this one. Now you just need to plug the value of x. You already know the x value. This is equal to 3 by 4 times LV minus C by 2. Just plugging that value, do the calculation by yourself. This is simple. You just need to multiply these 3 terms and taking this 2 as an LCM and then taking common and divide that 4. Okay, so you see you got 1.88. So this is the final equation, and inshallah in an example we will use this equation. Okay, this ends up, and in next lecture, that is lecture number 11, we do an example on it. So this lecture is all about the punching shear design. What is punching shear, how to control, you see different techniques, and in next lecture inshallah we will do example on these techniques. Inshallah we will design the column capital, we design drop panels, and we will design integral beam. Okay, so this ends up. If you have any question you can ask. Thank you for watching.